S. Chan presents educational video lectures. Difficult concepts made easy. Study anywhere, anytime.
Dear students, welcome to S. Chand Academy. I am Sameer Kumar and we are learning probability and statistics.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box.
We have seen binomial distribution in the earlier video, right? That was a discrete kind of a distribution. Poisson's distribution is another discrete kind of a distribution. Okay. Now, Poisson distribution is kind of a binomial distribution only, but under some scenario. Okay. We have learned in the binomial distribution that we took the example of tossing a coin 10 times and we have to predict or find out the chances of getting 2 tails or 5 tails. Okay, so that you can use for buying a lottery ticket also. Like there are suppose n number of lotteries, and then how many minimum number of lotteries you should buy so as to ensure yourself some chance of winning prizes. Okay, but sometimes in real life the scenario is not that simple. Okay, like the binomial distribution, tossing 15 times and getting the probability of getting 5 tails, so that is a very simple case. But in real life a scenario may be something like this. Suppose there is a huge gathering. Okay, there's a rally kind of a thing, or there is some kind of a mela, a fair. Okay, and there is like a gathering of 1 lakh people in that fair. Okay, and it's a very sunny morning, it's a very sunny afternoon, and people, there is a chance that people may get heat stroke. Okay, now as a administrator of the area or a doctor from the area, you have to take care of the well-being of the people. You want to analyze that, okay, how many people are going to get the heat stroke, okay, due to the huge gathering and high temperatures. You have to predict. So in scenario like that, suppose there is a gathering of 1 lakh people. Okay, and the probability of one person getting a heat stroke is something like this: P is equal to 0.002. Let's say this. Okay, the probability, not every person gets a heat stroke, right? But some persons, they get heat stroke, right? The probability of a person getting a heat stroke is this, and there's a gathering of 1 lakh people in that mela, in that fair. Okay, suppose someone says, what is the probability of 20 people? Probability that 20 people will faint. What is the probability that exactly 20 people will faint due to the heat, due to the extra heat? Now if I use the binomial theorem, it is going to be something like this, the binomial distribution. Okay, this becomes my n. Okay, so this is going to be C20 times 0.002 whole to the power 20 and 1 minus 0.002 whole to the power 1 lakh minus 20, whatever it be. This is the probability of 20 people from the fair getting the heat stroke. Okay, and if you have a medical arrangement for, let's say, 100 people, okay, near the mela, you have an arrangement for caring or tending to, let's say, 100 people. So you may be wanting to find out that, okay, what are the chances that up to 100 people, what are the chances that up to 100 people will need the medical care? You want to find out the chances, okay, that about 100 people will need the care, about the medical care. What are the chances? So like this, you'll have to, for this is for 20, you'll have to find out for other numbers also, okay, up to 100, let's say. So this becomes a daunting task, right? This itself, finding this is a complex thing. Okay, it's very complicated. Even if you use programming, it is going to run for some time. Okay, and then you have to add, for let's say you have to find for 100 people, you have to add all such numbers, okay, up to 100. Okay, that may be a little daunting. Okay, it may be a little difficult task. So what we do for such cases where the number is very large, okay, the number is large, okay, and the probability of the event happening is small, is comparatively very small, right? In those cases we do some approximation. Okay, we use limits, do some approximation, and try to simplify things, make life easier for ourselves. Okay, for n tending to infinity and p tending to 0, we do some limits, we do some approximation. Okay, under this scenario only, if I put in the limits that okay, n goes to infinity, n is a large number, and this probability p is comparatively very small number. Okay, so under these assumptions we try to simplify things. Okay, and that leads us to Poisson's distribution from the binomial distribution. Okay, we saw, after all, this is coming from the binomial distribution only, right? So we'll see how. So the assumption here is n is tending to infinity and the probability of the event is happening is almost zero, is a small number. Okay, but the product of these two is a fixed number. Okay, the product of n and p is a fixed number. Okay, n times p is equal to, let's say, lambda. Okay, lambda is a constant. Lambda is a constant. Okay, right. So if I write the probability for x, okay, let's take the probability this to be theta. Okay, p is tending to 0. Okay, np is this, right? P is the probability of that event happening. In the example that I took, the probability of one person getting the heat stroke. Okay, what is the probability of the event happening, individual event happening? Okay, so if I write it binomial distribution, if I write it as per the binomial distribution, Px can be probability of x be any random variable like 20 people, 30 people, whatever was the number in the previous example. So Px I can write as Ncx p to the power x 1 minus p whole to the power n minus x, right? This was it as per the binomial distribution assumption. Now you see here, this p can be written as p is equal to lambda upon n. Okay, p can be written as lambda upon n, right? Lambda is a fixed number, remember, is a constant. So this thing can be written as ncx. For p I will write lambda upon n whole to the power x and 1 minus lambda upon n whole to the power n minus x. Okay, now I'll try to simplify this, plug in those limits, n tending to infinity, p goes to 0. I'll try to plug in those limits. Okay, ncx is n factorial upon x factorial n minus x factorial, okay, times this thing. Okay, 1 minus lambda upon n minus x. Okay, now this thing here, if you see, n factorial divided by n minus x factorial will give you this thing, will give you n times n minus 1 times n minus 2. There was x factorial here, n minus 2 until n minus x minus 1. Okay, until n minus x minus 1 you'll have here left. Okay, this thing NCX can be written as this, okay? N minus 0, N minus 1, N minus 2, and until N minus X minus 1, okay? So NCX can be written using, NCX can be written like this, okay? From this one, from each of the terms, take out N common, okay? So I'll just remove this thing here. This thing here, I take out N common. How many terms are there? N minus 0, N minus 1, 2 until X minus 1. So there is X number of terms. Okay, there is X number of terms. So here, this thing will be equal to N to the power X times, this becomes 1, this becomes 1 minus 1 by N times 1 minus 2 by X, 2 by N, 1 minus 3 by N, and likewise until 1 minus X minus 1 upon N. Okay, this is this part here. There is an X factorial here in the denominator, and these are the things. Okay, I'll write it as they are written. Okay, lambda upon N to the power X times 1 minus lambda upon N whole to the power N minus X. This is what I have. I'll remove this. Right. I have to plug those limits. So now you see, this is lambda. Now all of these for limit n tending to infinity. For n tending to infinity, 1 by n is 0, 2 by n is 0, 3 by n is 0. So all these, they're all 1 each. 1, 1, 1. So this whole thing is nothing but 1. This thing becomes 1. Okay. So what I'm left with is n to the power x upon x factorial, and this thing remains here, lambda upon n whole to the power x and dot 1 minus lambda upon n whole to the power n minus x. Now you see, n to the power x cancels with this n to the power x. Okay, so I can remove this simply and this goes away. So in the numerator you have lambda to the power x left here, okay, multiplied by that thing. Okay, still I have to solve this thing. Okay, now this thing I can further split. Okay, this here can be written as, this is equal to lambda to the power x upon x factorial times, this thing can be written as 1 minus lambda to the power n whole to the power n multiplied by 1 minus lambda to the power n whole to the power minus x whole to the power minus x. Okay, I simply split the two terms here. Okay, erase this further. Okay, now see, 1 minus lambda upon n whole to the power minus x. Lambda upon n goes to 0. Okay, obviously you know how to put in the limits. This lambda upon n is 0. So this term here is 1. Okay, 1 to the power minus x or whatever is 1 only. So here this term also, this thing is also what? 1. Okay, that part becomes 1. So ultimately what I am left with is lambda to the power x upon x factorial multiplied by 1 minus lambda upon n whole to the power n. Right. This thing now I have to evaluate for limit n tending to infinity. N tending to infinity.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
So this thing is okay, but here I have n, I have to put in the limits. Okay, so just assume this part. Assume this part here. I have to figure out the limit for that. So I'm writing it separately. Let's say something y, okay, is equal to that thing 1 minus lambda upon n whole to the power n. Okay, limit is n tending to infinity. Okay, take log of both the sides. So ln of y is equal to n ln 1 minus lambda upon n tending to infinity. If I flip the n, 1 by n I write as h. Okay, so this becomes ln of 1 minus lambda h upon h tending to 0. Okay, use the L'Hopital's rule. This becomes 1 minus lambda h, and here you will have negative lambda. Okay, h tending to 0 is equal to negative lambda only. Okay, for h tending to 0, that is the value of ln y. So what is the value of y? That means y is equal to e to the power minus lambda, right? So this part here is nothing but e to the power negative lambda if I plug in the limit n tending to infinity, right? So what do I have ultimately? Ultimately px I have as lambda to the power x upon x factorial times e to the power negative lambda. This is the probability for the random variable x for a Poisson's distribution. This is the, and this is just an approximation under the limits that n is very large, probability of each event is very small. Okay, under these assumptions, and the product n times p is a fixed number, lambda is a constant lambda. Okay, right. So in binomial distribution, the mean is given by n times p. So lambda is kind of mean. Okay, lambda is kind of mean of the distribution, right? So we have seen how we have arrived at the expression for the Poisson's distribution, okay, starting from the binomial distribution, okay, under the given assumptions, right? But again, the question arises that where and how is this going to be useful for us, okay, right? So we'll see, take a practical scenario where this information can be applied to our use, okay, fine.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.